So the goal of this session is to learn more about buffers by calculating the change in buffer pH when a small amount of a strong acid or base is added. We're going to focus on acids in this session, but you can figure out how it would work the same for bases. In a previous problem, we worked out that if you prepare a buffer by dissolving 0.200 mole of NaH2PO4 and 0.100 mole of NaH2PO4 in enough water to make 1 liter, that the pH of that solution equals 6.91. We also figured out that the pKa for this acid-base pair is 7.21. We're going to need those later. Okay, so our new question is, what is the pH of that buffer that started at 6.91 if we add 0.005 moles of HCl to that solution? So we're going to see the way the buffer resists the change in the pH of the solution. Okay, so remember that our Ka2 refers to 0.0 H2PO4 minus plus water goes to HPO4 2 minus plus H3O plus. Okay, and you know that by Le Chatelier's principle, if we add extra H3O plus to our reaction, that the reaction is going to shift from if we add more of a product, we're going to produce more of the reactants. So the solution is going to get a little bit more acidic. One thing to think about here is that when we add HCl into our solution, that HCl is a strong acid. So it's going to dissociate completely to form H3O plus and Cl minus. The Cl minus doesn't affect the pH of the solution, but the H3O plus will, because, as we said, it can react with HPO4 2 minus. So let's look at that reaction. We can divide this problem into kind of two major steps. The first step is that we need to think about how the strong acid neutralizes some of the weak base form. So we can write that chemical reaction as HPO4 2 minus, the weak base form, is going to react with some of the H3O plus, or with all of the H3O plus that comes from adding HCl. That neutralization reaction will proceed to completion to form H2PO4 minus and water. Okay, so this, we said, is the reaction between the base form and some added strong acid. Okay, if we think about the stoichiometry here, we start with 0.100 mole of HPO4 2 minus, and we said we're adding 0.005 mole of H3O plus from the HCl. That means that the H3O plus is limiting. So we're only going to use as much H3O plus as we have, and we see that all the coefficients are 1. So from the reactant side, we're going to lose 0.005 mole of HPO4 2 minus, and we're going to lose all of the HCl, of the H2O plus. We started with 0.200 moles of H2PO4 minus, and we're going to gain 0.005 mole when the H3O plus reacts with the HPO4 2 minus. Okay, so after that neutralization reaction occurs, we're going to be left with 0.095 moles of HPO4 2 minus, no leftover H3O plus, and 0.205 moles of the weak acid form, H2PO4 minus. Now, the second part of this is to recalculate the pH of the solution. And that we use the Henderson-Hasselbalch equation. The pH equals pKa plus the log of the base form, HPO4 2 minus, over the acid form, H2PO4 minus. All right, so that's going to be 7.21, we worked out the pKa, plus log of 0.095 moles per liter, because these are each in 1 liter, divided by 0.205 moles per liter. Okay, when I do that, I get that the pH equals 6.88. Okay, so let's compare that to the initial pH of the buffer. We said before it was 6.91, and now it's 6.88. So that is a delta pH, a change in the pH of negative 0.03 pH units. So just the difference there. To drive home the message of what a buffer is actually doing, we see that the 0.688 and 0.691 aren't exactly the same number, but they're really close. Let's consider what would happen instead if we just added that 0.005 moles of HCl to neutral water. In that case, we would once again have that the HCl plus water dissociates completely into H3O plus and Cl minus. In that case, if there wasn't any buffer, then the concentration of H3O plus after the dissociation equilibrium would be 0.005 moles in 1 liter. Okay, if we calculated the pH of that solution, we'd get negative log of the H3O plus concentration, so 0.005 molar, and we'd see that the pH equals 2.30. Okay, so the delta pH in this case, if we add 0.005 moles of HCl to neutral water, then neutral water started at pH 7. So that's a change in negative 4.7 pH units. So a buffer buffers by keeping that ratio of the weak conjugate acid form and the weak conjugate base form pretty close to 1. And you see that while the pH does change a little bit when we add a strong acid to the buffer, it is a very small change compared to the change we see if we add that strong acid or base to an unbuffered neutral solution.